Hello everyone. Today we'll be going over the properties of matrix operations. So, in the last few videos we concentrated on the mechanics of the three basic matrix operations. We did matrix addition, scalar multiplication, and matrix multiplication. In this section, we're going to develop the algebra of matrices. And you're going to see that there are a lot of parallels between algebra and its properties of real numbers. Before we do so, let's begin with a couple theorems, or postulates, as I would say. Okay, before I dive into the properties of matrix addition and scalar multiplication, let's establish a few rules here. Let's say that A, B, and C are m by n matrices, and values C and D are your scalars, and therefore the following properties will be true. So starting from 1 to 6, A plus B, when it comes to matrix operations, does the commutative property of addition apply? And if you were to say yes, you would be correct. Now, let's say we have B and C enclosed in parentheses with the addition of A. What happens if we were to switch... What if we were to switch A and C, where A is in the parentheses and C is outside the parentheses? Would those two values be the same? And if you said yes, then I would like to ask you a follow-up question. Which property would it be? Is it still the commutative property? And if you said yes, well, got you there. It's actually the associative property. Now, the third one is also the associative property, and it's simply associative property pertains to variables switching within parentheses and out of parentheses. And in this case, it applies to both matrix addition and scalar multiplication. Now, for 4, 1 times A, we know what A has to be. It has to be 1. And therefore, this falls under the multiplicative property. And looks like I went a little out of order. My bad, guys. Let's look at number 4 this time. So we have C times parentheses A plus B. Now, what happens if we were to distribute our scalar? What would that produce? And if you said it would produce the distributive property, you'd be correct. Now, would number 6 also fall under the distributive property? And at this point, you guys might already know the answer. The distributive property applies. So these 6 theorems are going to be integral for the next examples that follow. So in this example, we're going to be adding more than 2 matrices. And whenever we're adding matrices, we always add the corresponding entries. And it's as simple as 2 plus 2. So if we were to add up row 1, we would get 2. And if we add up row 2, we would get -1. That wasn't so bad now, is it? Now, this opens us to something new. One important property of the sum of real numbers is that 0 is what's known as the additive identity. That is, C plus 0 is equal to C, where C can be any real number. This principle applies to matrices as well. Specifically, if A is a matrix that is m by n, and we have a 0 identity, with the same dimensions, we get a zero identity with the same dimensions consisting entirely of zeros. Therefore, our coefficient matrix plus our zero identity will equal A. So the 0 sub mn is our zero matrix, and it is our additive identity for the set of all m by n matrices. So for example, let's say our zero matrix was a 2 by 3. It simply means that it's a 2 by 3 matrix consisting of all zeros. When the size of the matrix is understood, you can denote the zero matrix simply by either O or 0. I'll usually go with the latter. We're not going to prove this. Well, yeah, we're not going to prove this because the system in matrices, it applies to real numbers as well. So if you were to switch B in our theorems for 0, they're going to equal. So let's not waste our time. But what we can do, we can do one proof. We can do one proof for this example. So for a real number, let's say x plus b is equal, let's say x plus a is equal to b. This is a real number. We're using real numbers. So, and we're solving for x. And let's say we subtract a on both sides. Get x plus a minus a equal to b minus a. Therefore, we have x plus 0, which is equal to b minus a. And we end up with x equal to b minus a. Once again, these are for real numbers. Now we're going to do something very similar, but with matrices. M by n matrices for x. M by n matrices where we solve for x. So we have matrix x plus matrix A is equal to matrix B. Let's subtract A on both sides. Get x plus A minus A is equal to B minus A. Then we get x plus 0 is equal to B minus A, and x simply becomes B minus A. And there you go. We have confirmed the similarities between real numbers and matrices. Okay, so in this next example, we're going to be solving a matrix equation. We are given the objective of solving for x in the equation 3x plus a is equal to b. We are given our a value and b value and an equation. So let me ask you guys, what do we do first? And think back to, I don't know, high school algebra. And if you were to say we solve for x given the equation, you'd be correct. In this case, we subtract a on both sides, and we divide by a third for both sides to isolate x. Therefore, we get x is equal to 1/3 times b minus a. And given the matrices that we were provided, it is x is equal to 1/3 times the matrix -3, 4, 2, 1 minus 1, -2, 0, 3. From there, we can incorporate matrix subtraction, and we get -4, 6, 2, and -2. And then I'm going to ask, what's next? What is the final step? And remember, our 1/3 is a scalar. And one more question. What property are we using in this step? If you said we're using the distributive property, you would be correct. And you would know that we would just distribute the 1/3 into each entry. So the matrix will look something like this. And there you have it. We have now just solved a matrix equation. Okay, so in this example, how do we find the matrix product of A, B, and C such that we can prove that this equation exists? Now, fundamentally, this example is asking us to prove the associative property of matrix multiplication. Fundamentally, as we've already gone over the theorems, we should know that those two terms do exist. And all that's asked of us is that we prove it. So, let's start with parentheses AB times C. And I hope you guys wrote down the matrix, and if you didn't, that's fine. I'll run for you. So let's write down our matrices, and we have 1, 0, 2, 3, negative 2, 1 times C, which is negative 1, 0, 3, 1, 2, and 4. We're going to multiply two matrices within parentheses as ruled by PEMDAS. Always remember to multiply each row by each column. And when you do that, you get a matrix product of negative 5, 4, 0 in the first row, negative 1, 2, 3 in the second row. And the C matrix will stay as is for now. And now it's your guys' time to shine. When I multiply these two matrices together, what is the product? What's the dimension of our product? Okay, so we have a 2 by 3 matrix, and we have a 3 by 2 matrix. Our 3's are in the right place, and therefore our matrix should have 2 columns, 2 rows, and 2 columns. Perfect. And if you guys already figured it out, good job. And multiplying the matrices, we get 17, 4, 13, and 14. And that's equal to AB times C. Sweet. Now let's confirm the other term. And we're going to write down our matrices, including the ones in parentheses, 1, 0, 2, 3, negative 2, 1. And then we're going to finish this one up. Okay. So let's follow the rules of PEMDAS for this one. Let's multiply two matrices within the parentheses, and we should get a 2 by 2 matrix. And once again, it's going to be the same. It's going to be the same as the other term. And if you guys are wondering, how is he going so fast? Well, I have a graphing calculator right next to me. They are a great investment. And there you go. We have proved that even when both products A, B, and B are defined, oh, never mind. That's for the next example. Don't worry about it. Okay. In the last few videos, we established that you can't multiply two matrices if their dimensions are different. However, in this example, we're given two matrices of the same size. Conversely, does that mean AB is equal to B times A? And keep that question in the thought of your head. And to solve that question, it's just gonna take some elbow grease. We have AB, which is 1, 3, 2, negative 1, and the B matrix is 2, negative 1, 0, 2. That was weird. And when we multiply each row by each column, we get 2, 5, 4, and negative 4. Okay. Now let's do B times A, where we get 2, negative 1, 0, 2, times 1, 3, 2, negative 1. And you're going to notice something a little funky. 0, 7, 4, negative 2 is our matrix product. However, the matrix products AB and BA, it's not like they're never equal. Sometimes they can be equal. So for example, let's find AB and BA for the matrices below. Okay. Quick clarification. The commutative property fundamentally does not apply to matrices. It doesn't. It looks like the textbook likes to overcomplicate things. Oh, my bad, guys. Okay. In this example, we have, let's say we're given an equation. AC is equal to BC. We can factor out C on both sides, and we divide C on both sides, we get A is equal to B. What if I told you that wasn't always the case? And we're going to uncover that in this example. So, let's confirm that AC is equal to BC. So we have matrices A times C, which is equal to 1, 3, 0, 1, times the matrix 1, negative 2, negative 1, and 2. And if we were to multiply two matrices, we get negative 2, 4, negative 1, and 2. Now let's do the same for BC. We get 2, 2, 4, 3 times 1, negative 1, negative 2, 2. As a result, we get the same as the matrix multiplication of AC. And look, see? We have confirmed that AB is equal to AC, even though hold on, this is supposed to be, this is supposed to be AC is equal to BC, even though A does not equal B. This is an example where cancellation is not valid. And in this example, we are opened up to a special type of square matrix, one that has ones on the main diagonal. So let's say we have I sub n, where I is a matrix consisting of a diagonal of ones and all the entries are zeros. So we get 1, 0, 0, 0, 1, 0, 0, 0, 1, and so forth and so forth, where n can be as big as you can get, and the overall size of the matrix will determine the norm of the diagonal as well. So if n was equal to 1, we would get a 1 by 1 matrix, and if n was equal to 2, we get a 2 by 2 matrix. And what happens if n was 3? And if you said it was going to be a 3 by 3 matrix, you are stinking right. Yes, that is correct. And of course, you get a diagonal with 3 ones. When the order of the matrix is understood to be n, you can denote I sub n as I. And the value I sub n would serve as the identity for matrix multiplication. It's just the identity matrix of the order n. This video is going to be split into part 2 because the next part is going to be wickedly long. So, as a benefit to you guys, I'm going to split this video into 2 parts, so that way you guys can understand the material efficiently.